All right, so what I have here is I have a column filled with water, and I have some universal indicator, which is a mixture of bromothymol blue, phenolphthalein, and methyl red. All right, so I'm going to add a little bit of base. All right, how low can I go? So a little bit of base should make my color change go to a little bit of a bluish area. Okay, so I'm going to make this slightly basic. As you can see, the color change occurs. A little bit green on the bottom, but that's cool. Now, I got a little bit more basic on top, and I can add some more if I'd like, but I think I like that. Now, what's cool is I want to add an acid to this, so I want to add CO2. All right, so I know CO2 is a Lewis acid, right? We learned about CO2 has a what? Double bond, sp what hybridized? sp 2 domains, right? Because oxygen is more electronegative, it pulls the electrons away. So this becomes a little bit of positive. So when I drop this in water, hey, okay, the lone pairs of water get pulled in, and we make a carbonate by that mechanism. So this is a lone pair acceptor, okay? And what's this going to lead to by a mechanism? It's going to lead to the H2CO3, which is hydrogen carbonate, which is going to dissociate into an H+, which is going to drop the pH, and the bicarb ion. We know that CO2 is acidic. Okay, so we want to drop CO2, and CO2 in the air is hitting it, but I want to make CO2 solid. Okay, so that's kind of cool since we're talking about intermolecular attractions. What I have here is I have a tank. Let me show you what that looks like. And so there's liquid CO2 in here. And what we're going to do is, obviously, it's connected. I'm going to bring it into a box. But here's the cool part. I've got this tube that runs all the way down the middle. Poor planning on my part. Okay. And because it's under pressure, the pressure is going to push the liquid into this tube. So when I release the hounds or the valve, okay, the pressure and open it up to the atmosphere, the higher pressure is going to go where? To the lower pressure. So the higher pressure is going to push the liquid into this tube, and I'm going to be putting drops of liquid or Jupiter into this little box. That's what this is right here. Okay, so I've got this box here. All right, I'm going to move this tube for right now purposes so we can see. And I got this box, and you know, like a good magic show, you got to show that there's nothing in the box, right? So I've got myself an empty box. Okay, and I'm going to put. And this is not magic, by the way. Maybe I'm very. There we go. Ah, there we go. So there it is. Smooth operator I am. Okay, putting the top on. All right, and what I'm going to do, clamp it shut because the pressure is going to build up a little bit. I'm going to shoot liquid into this container here now, and magically, I should make some dry ice. Except this seems a little. Oh, we'll see what happens. So, any case, without further frost. Sorry. All right. Turn this on. You can actually see some frosting going on. Now, does CO2 have any intermolecular attractions for itself? Zero? It's non-polar or polar? Is that symmetrical CO2? Yeah, so what kind of intermolecular attractions does it have? London dispersion forces. It's becoming a solid, people. It's attracting itself. It has to have intermolecular attraction. Is this an ideal gas or a real gas? Yeah, all gases are real. And if you're going to see a solid appear, okay, we know that this guy, okay, and there's my box, and it's not empty anymore. Okay, I got myself a white solid. And it's not completely a block, but we're we have here is some good amount of dry ice. We call it dry ice because CO2 likes to sublime. Okay, it's also a very brittle solid. Molecular compounds are brittle, right? So they break up into little pieces very easily. Okay, but the demo here today, and so before I continue with this demo, how did it go from a liquid to a solid? By the way, it's called the fusion tube. All right, but how does it go from a liquid to a solid? How did it? And by the way, a liquid to a solid, how did it freeze? Well, as this liquid hits this air, it immediately became a gas. So actually, it didn't freeze. So when the liquid droplets hit, we know that because the attractions for CO2 molecules are extremely weak, okay, it becomes a gas. So actually, this liquid evaporated into a gas. Now, as it evaporated to a gas, stick with me for a second. Here's the little CO2 molecules. Do you think they expanded out from the liquid? So here's a liquid droplet, and it's becoming a gas. Do you think it's expanding outward? Do gases have more energy than liquids? So as it became a gas becomes and can move hundreds of miles an hour. This gas was expanding away. You have a concentrated source of a liquid, you're producing a gas around that little droplet, the gases are expanding outward. Here's the cool part. If the gases are expanding outward, aren't they overcoming their intermolecular attractions for them to expand outward? Oh, so as these gases were expanding outward, they needed to absorb energy from their surroundings to do so. Because in order for them to expand outward, they had to overcome their van der Waals or their LDF forces they had for each other. So the expansion of gases is called the Joule-Kelvin effect. Okay, it's why your refrigerators make a cold solution. We have gases that are expanded in what we call a expansion valve. Okay, so you guys kind of know this because when I push down on a fog horn, my fog horn is gone now, it gets cold. Or if you ever used a hairspray bottle, I don't know, if you use it a lot, what's it feel like? It feels cold. Because you're expanding what? A liquid became a gas, which is the aerosol, and as it expands, it overcomes its intermolecular forces. It acts more like a ideal gas as it expands outward. Expanding gases require energy. They're overcoming attractive forces. And if you have to overcome some force, it's not a bond, you need energy. And we took energy from the air. It's an endothermic process. So in this area, as gases expand, as they needed energy to overcome their attractive forces, they took it from the surrounding area. And as you take energy from the box, inside the box got so cold, the gas went straight from a gas directly to a solid. What's that called? No, a gas directly to a solid is what's happening, could happen to us by noon today. Snowing, deposition. Now, this weak solid, okay, which we know is a Lewis acid, is it blue up top? I'm not good with the colors. Is it blue enough? I don't know. So let's make it a little more bluer on top to make it a little more basic. And now I'm going to add some Lewis acid. I don't know if you can see, but what's happening to our colors? Yeah, because we're dropping an acid. I'm trying to get the full rainbow effect here. But so as by the top, I should have more redder solution, okay? And let's add some more Juder juice, okay? And so the energy that I'm giving to the dry ice is making it sublime. And this is what you have always in the background when someone's teaching something in science, right? Except today I'm actually teaching about this. Now this is sublimation. They call it dry ice because it skips the what? Liquid phase, because it has what kind of intermolecular attractive forces? Weak, so weak that this molecular substance goes right to the gas phase. Also, we learned about phase diagrams, right? One more thing about phase diagrams to teach you this is that we talked about phase diagrams. Let's look at CO2. All right, I've got myself a solid. as the temperature increases, I jump directly to the what? Gas phase. These are called the sublimation line. And it's because that triple point line is so high. Right? This is about 5 atmospheres. We would need 5 atmospheres of pressure for CO2 to be liquefied. In here, without melting it, it's melting. Okay, break some, hiya. Okay, put that in there. Okay.
I have no idea what you're saying. I'm a little distracted. Whoa. It's sticking to your hand.
There we go. Satisfying. Because CO2 is more dense than what? Air. That's why they use it as an extinguisher for fires. There was too much pressure early on. Okay? So a little bit of fun we can have with CO2. Okay? But in any case. That's called the CO2 fountain. Boom. Okay.